Welcome back, Physics Dirty. This is the CO1.7 power section, and it's the last section of CO1, conservation. So in this one, we'll define power in the scientific sense and solve word problems involving work and power. So first of all, power is defined the rate at which work is done. So in other words, how fast you can accomplish a certain amount of work. Average power equals the work divided by the time to do it. So obviously, if you're looking at a rate, you're looking at how it's done per time. So work done per time. And of course, work is force multiplied by displacement. But as we also saw, work is also change in energy. So the amount of energy transformed. W equals delta E. So of course, that delta E could be EK or EP. So change in kinetic energy or change in potential energy. And how fast that is occurring is what power is. So the power rating of an engine refers to how much chemical or electrical energy can be transformed into mechanical energy. The SI unit for power is, of course, work is joules, time is seconds. So joules per second, which has the combined unit of watt. Okay, so W-A-T-T. We are most familiar with the watt for electrical devices, such as the rate at which an electric light bulb or a heater changes electrical energy into light or thermal energy, but the watt is used for everyday types of transformations as well. In the British system, the unit of power is the foot-pound per second. For practical purposes, a larger unit is often used, and of course that is the horsepower. 1 horsepower is defined as 550 pounds per second or 746 watts. So that's kind of the one that we'll be looking at. 1 horsepower is equal to 746 watts. So if we're converting from one to the other, we have 746 watts per horsepower, or vice versa, of course. 1 HP is 746 watts, so we can convert from one to the other. To see the distinction between energy and power, consider the following example. A person is limited in the work that he or she can do, not only by the total energy required, but also by how fast that energy is transformed. That is, by power. For example, a person may be able to walk a long distance or climb up many flights of stairs before having to stop because so much energy is expended. On the other hand, a person who runs upstairs may feel exhausted after only a flight or two because he or she is limited by, in this case, power, the rate at which you can transform that stored chemical energy in your body into mechanical energy. Okay, on the next side, there's an example here doing just in fact that. 60 kg jogger runs up a flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. Estimate the jogger's power output in watts, then in horsepower, and then how much energy did this require. Okay, so if we're looking for power, so power is equal to work over time. Okay, now work is force multiplied by displacement over time. And in terms of force, the type of force that someone has to exert, of course, is going to be equal and opposite to Fg. So we could say Fgd. And of course, Fg is mass times gravity. So we could substitute, and realize that this little g here is a subscript g. So I should have made that a little bit more clear. So I'm just going to fix that up. So F, make a little g, Fg, because here I'm going to put in the big G. So substituting that in. And of course, when lifting up. So we know, of course, we would analyze this situation vertically. F net is equal to F plus Fg, and realize that F net is 0, solve for F, and we get a positive number. So we could combine that into one step if we treat G as positive 9.8, like we've been doing before. So 60 kgs, 9.80, a vertical height of 4.5. This is all done in 4 seconds. 661.5 watts. Quite often it's better to write out the whole word for watts as opposed to W, so we don't get it confused with work. 2 sig figs, I think, here, so 660 watts. Okay, and if we look at that, what that is in horsepower, 660 watts, and of course, going from watts to horsepower, 746 watts is 1 horsepower. So if we work that, that works out to be 0.88 horsepower. So just shy of 1 horsepower. So that kind of gives you an idea of what a human being would be able to do. B, how much energy was this? P over T. Now, of course, recall that W is change in energy. So we could substitute it, I guess looking like that. Multiply each side. So work is change in energy. Power multiplied by time. If I use the non-rounded version here, 661.5 multiplied by 4 seconds, that's going to give me 2,646 joules, which is 2,600 joules rounded off. Okay, so that gives you an idea of some common values that you would use for that. Automobiles do work to overcome the force of friction and air resistance to climb hills and to accelerate. A car is limited by the rate at which it can do work. Let's highlight that. So the horsepower of the car, the rate it can do useful work, and of course they're rated in horsepower or kilowatts. Car needs most power when climbing hills or when accelerating. In the next example, we'll calculate how much power is needed in these situations for a car of reasonable size. Even when a car travels on level road at constant speed, it needs power just to overcome all of the forces working against you, the retarding forces, to maintain that constant speed. So if you're traveling going 110 kilometers per hour, you do have to have a certain amount of power to go against all the forces of friction and air resistance that are working against you. These forces depend upon the conditions and speed of the car, but typically range in between 400 and 1,000 newtons. It's often convenient to write power in terms of the net force applied to an object and its speed. This is readily done if we look down here. Almost alluded to it up above. So work is equal to force times D. Quite often I put deltas here just for change in. So W is equal to force multiplied by displacement. So if we look at that, F times D over T. And as you recall, from very earlier in the course, average velocity is equal to change in D over change in T. So power can be expressed as force multiplied by constant velocity, because that delta D over T is equal to V. So that's another equation you can write down there for force. Okay, so we have the example next. We're running out of time on this video, so I think I'll put it on the next video. Okay, so tune in to the next one to go through the car example, and we'll see you then.